All right, I wanted to spend a minute and talk about how stack allocation works in the context of tasks. And really, this is how stack allocation works just in the context of functions, but in tasks you need to better understand that so you can reserve space for each of your functions in each of your tasks. So I've got the stack.c program open. I've set a breakpoint. We're right here at this await coroutine spot, and what we're going to do is walk through and watch stack usage. Obviously, Blink main hasn't been called yet. It's got 504 bytes of free space. I can track my stack usage by looking at the value of wreg15 or w15, the stack pointer. Since we're in main, I'm not concerned about main stack usage. We're going to focus on stack usage of the Blink coroutine. So I'm going to trace into this and sort of skip through a lot of this until we finally get to that Blink coroutine. So we're just going to walk through this. This is the moment, this long jump coroutine is the moment when we will switch to the Blink coroutine. So now we are in the Blink coroutine, and it looks like my initial value of my stack pointer is 13B2. That's W15. And if I look over here in memory, you can kind of see 13B2. There's some data there. It looks like it's already from other functions being called. A couple things have been pushed on that stack already. We need to keep a good track of that stack usage. And to do that, what we're going to do is just put together a quick spreadsheet. So I've listed at task start, this is the Blink task. Then W15 sits at 13B2. That's sort of our initial value. And we're going to track how that changes as the function executes. All right, so we're going to step through this code one line at a time. And what's really important to us is right here, this is a call of the Blink main. It's a little bit hidden in the way that the function call is done, but the important thing for us is we're at 13B2 right now. The moment I trace through this, it's going to call our Blink main function. I'm going to do that now. Watch my 13B2 change to 13B6. So let's update that in our spreadsheet. All right, I've typed that into the spreadsheet. We've got the space allocated. Every function call will cost 4 bytes of memory on the stack. Every function call on every task costs that. So we just need to understand what that is. So here we are. Our stack pointer is at 13B6. To get a better idea of what's happening, I actually would like to look at the raw assembly behind this function. So to do that, I've pulled up the disassembly for this Blink main function. And notice the very first thing we're going to do is this assembly instruction called link2. What the link instruction does, not one that we covered in the previous assembly part of the course, is help the processor allocate some space on the stack. So it's going to do two things essentially. First thing is it's going to save W14, which the C compiler uses to access local variables in temporary space, onto the stack. Then it's going to allocate however many bytes you asked of it on the stack by incrementing W15. So when I say link to, it's going to cost me 4 bytes. It's going to be 2 bytes to save W14 and then another 2 bytes for the 2 bytes that it's requesting for stack space. So let's watch that happen. We're at 13B6 right now. I step 1 assembly instruction and now we're at 13BA. Why did it need that? Well, it's got one local variable, an integer I value. As you know, an integer takes 2 bytes of space. That's why the C compiler asked assembly to reserve 2 bytes of space for it, plus the 2 bytes to save the old W14 register. Let's update our spreadsheet. So the space for I value, that was 2 bytes, and the space for, W14 is a total of 4 bytes of space, so our W15 is up to 13BA now. Let's watch as we execute this. As we go through, mainly we're interested in the value of that stack pointer and does it change. As we go through most of this code, we're toggling the LED. That's not changing, but the moment we get to this call a subroutine, we know that calling a subroutine always costs 4 bytes. So here we go. We're going to trace into that, and we see the stack pointer go up to 13BE. Again, let's add that to our list. So I put the call to yield coroutine. Now we've allocated a total of 8 bytes so far in our task, and we're now ready to call the yield coroutine function. Inside yield coroutine, it needs a little bit of space. It definitely needs 2 bytes of space here for the I value, plus the C compiler decided it needed an extra 2 bytes of space, probably because it needs to do a bit of calculation further down in the function. So it's going to allocate 4 bytes of space for the parameter and local variables, plus it's going to need 2 bytes of space when that link instruction executes to save the previous value of W14. So a total of 6 bytes gets allocated right there. I'm going to trace that instruction by hitting F7, and we'll watch our stack go up from 13BE to 13C4. Let's update our table. So again, yield coroutines needed 6 bytes of space for its local purposes. 2 bytes for I value, 2 bytes for whatever local variables it had, and 2 bytes to save the value of W14, which will be restored when that function exits. Again, we're going to walk through this function, mainly keeping an eye on that and look for any other function calls that yield coroutine makes. So we'll just kind of zip through this. And so far, that hasn't changed. We're still at 13C4 until we get to this point. We're ready to call the goToCoroutine function. So we're at 13C4. We call the. So here we are in goToCoroutine. So again, let's add that to our stack. As always, every time you call a function, it costs 4 bytes of stacks. So we're now at 13C8. Plus, goToCoroutines needs 2 bytes for this variable, plus another 2 bytes for this variable, plus another 2 bytes for its internal processing, plus 2 bytes for W14. So as the moment we execute that link instruction, we see it go from 13C8 to 13D0. That was a total of 8 bytes of stack that goToCoroutine allocated. Again, we'll update our spreadsheet. So you can see, again, this is taking a fair amount of space. We took 8 bytes of space. We're now at 13D0 inside that goToCoroutines function. Now we're ready to walk through goToCoroutines and look for the next function call that it gets executed. To get a slightly higher level view, rather than stepping through the assembly, what we'll do is step through the C. None of these asserts requires a function call. setJumpCoroutine does require a function call. However, that function will return to us, so we won't see any difference when we trace inside it, although it does mean that stack got used. So if we simply bypass this, we won't notice it. We do want to step inside this. So here we are getting ready for the function call back in the assembly side. We're going to call this setJump function. And notice that we have to go over here and watch the assembly happen here because we just don't have any source code for that function. That's a library function that Microchip doesn't provide their source for. So you'll notice that we just went up to 13D4. Some stack got used there because of that function call. Again, we'll update our spreadsheet showing the 4 bytes that the call to setJump is using, pushing us up to 13D4. And now we'll step through that function and watch it do things, but notice our stack value is not changing. So even though it's doing lots of work, it's not requiring any additional memory on the stack. And in fact, we're now at a return function, so we'll see after the return that value goes back down to 13D0 after the return. And again, we'll update the spreadsheet. Now, remember, we use this space, so I'm putting the -4 here just to show that the space was deallocated or that we went back down, but that space still needs to be reserved so that it is available for setJump. In other words, we don't get to subtract the overall space. We still need these 4 bytes of space when we define room for this task. Let's switch back and watch what happens next. For a slightly higher level view, after we're done with this setJump, we'll continue tracing. The set stack limit function, again, this is something a bit low level. Over on the assembly side, we'll notice what happens. Even though it looks like a function call, it just turns into two move instructions, and our stack is not allocated in this. So we'll just step through those two. And now we're ready to call this long jump function. Again, remember that long jump will require us to allocate some stack. We're going to trace inside that. Again, we're at a place where we don't have any source code for, so we have to just follow it here in the assembly side of things. But notice inside this set jump function, we did go up to 13D4 because of that R call. So we're going to put that on our spreadsheet. And so you see now we're back up to 13D4. Notice that in the call return we allocated and then we're able to reuse that same space with a call to long jump. So when one function calls another, you have to add the stack allocated. When a function is called, returns, and then another function is called, it's going to be the maximum of the stack space allocated by those functions. So again, we've used from 13B2 all the way up to 13D4 thus far. Now we're ready to go through that long jump call and make sure that our stack doesn't go beyond 13D4, and indeed it won't, but we'll walk through that. So we'll let the long jump do its job. And at this point, the stack is going to change, but what's happening is it's simply switching back to a new task. And so this isn't stack space that's counted against our current task. Instead, we'll find ourselves back in the main task, if you remember that value from earlier, and we've completed our analysis of the stack space used by the blink task. And so if we at this point simply run the program to see what happens, notice that our blink main next reports 468 bytes of free after we went through all those stack calculations. Let's think through the math. That was a total of 34 bytes if I just add up all this in my nice Excel formula there. Our initial space was 504, we had 468 after, we subtract the 2, and you can see the stack is very similar. There was probably 2 bytes allocated initially at 13B0 when we first entered the subroutine. So notice what costs the space. Every time you call a function, it costs 4 bytes. Functions like blink main that called functions, that called functions, that called functions, add that stack usage up. In addition, notice that inside each function, it'll typically need some additional space for local variables, for parameters, for storing that W14 register. So simply calling blink main wasn't just 4 bytes, it really took 8 bytes of space on the stack for the baggage that comes with it. Likewise, yield coroutine took 10 bytes of stack space if you include all the local variables it had, or for goto coroutine, 12 bytes of stack space. And since blink main called yield coroutine, which called goto coroutine, which called set jump, it's the sum of all those stack spaces, which can add up quickly to, like I said, a total of between, depending on how you count it, 34 to 36 bytes. So this will give you a better idea of how to allocate stack, where that memory is going, and what to pick for that number. Be careful, don't allow the stack to overflow because bad things happen to your program and it does become rather difficult to debug. Always give yourself plenty of space and think about how functions are calling functions, and not just how many, but how much space does each of those functions need, which can far dominate the 4 byte cost of calling with cost space for their parameters and local variables.